Hello, welcome back. So we have seen so far two ways to represent rotations in 3D, and they are, well, rather complicated, not as easy as rotations in 2D, I would say. Today we will be continuing describing rotations with yet another two types of representation. And we'll see how they are related to the previous one and what are their pros and cons. So one thing, let me do this so I can do that. So we have seen so far two concepts. One is rotation matrix, and Euler angle, Euler angles. So rotation matrix is excellent in my humble opinion. It is robust. It is very easy to work with in terms of computations in a computer. It's a matrix. You can multiply your whatever vector. It rotates it. It is very good. The only couple of downsides that it has is one, a rotation matrix as a whole is not very easily interpretable. And if you look at it, you don't know what it means. A rotation matrix may look completely similar to something that is not even a rotation matrix. And also it has 9 elements, 9 numbers in it. And it is not, one thing, it is redundant. So you only, in principle, in theory, you need 3 numbers to express 3D rotations, but having 9 is way too much. And also, when you want to discuss dynamics in terms of equations of motion, rotation matrix doesn't fit very well in that kind of formulation. Euler angle was excellent in another way. Excellent because it is very easy to interpret and it is very engineering mindset behind it. So you can have literally joints, put one after another, revolute joints, and that would create your 3D joint, or that allow you to do 3D, and perfectly fine. You can define any of those angles or those angles as your generalized coordinates and continue building equations of motion with that. A very big issue that often comes actually annoying is Euler angles have something called singularity, or maybe you have heard of a different term for that, a gimbal lock. And that is when the two of your axes that you're rotating about are aligned. Then you run into issues that velocities may be discontinuous, and at that particular orientation, you cannot properly define Euler angles. And another potential downside of Euler angle was if you have one Euler angle, one set of angles, and you rotate your body, the rotation finishes, and then you want to rotate it again with another set of angles. Combining those two is a little clunky. You have to essentially build the rotation matrix of the first one, rotation matrix of the second one, and then multiply those matrices together. So in that sense, it has its own challenges to work with. Today we'll be talking about two very related ways to describe it, that they are kind of a compromise between the two, between rotation matrix and Euler angles. And instead of working with 9, instead of working with 9 in rotation matrix and working with 3 in Euler angles, which is almost enough, but not quite enough. We work with a different representation that takes 4 parameters. So slightly more than 3, And because of that extra parameter, now they don't have the singularities that Euler angles have. They are more or less easy to interpret, these new ways we are going to deal with. And it is, in some sense, easier to combine successive rotations with those new methods. So the first one that we'll be looking at in this video is something called usually axis and angle. So this is like probably everything else in 3D rotation is the work of Euler, and it is based on a famous, one of the fundamental theories in rigid body rotation or orientation, and that is Euler. Let me do this. Euler theorem. He has a lot of theorems, but this one is, it says, let me, so I'll put a star. Any rigid body displacement with a fixed point. So I'm going to underscore that, is equivalent to a rotation about some axis that passes through that point. So what it says, imagine any body, or essentially a frame, but let's look at the body. The body moves around, but one point on the body remains fixed, remains in one place after the displacement. So considering that case, the motion of body could be arbitrary, could be anything, can be represented by just a single rotation about one particular axis. So if I try to visualize it, I have a beam like this, and it rotates in 3D. Maybe looking at it from a different angle, it even looks different. But one point on the body remains fixed. What this theory says, this displacement can be represented as just a single rotation about one axis that passes through the point. So if I also fix a reference frame to the body, this is my body fixed reference frame, it probably rotates and becomes, I don't know, that. They look too similar. Let me change it. Undo. Let me draw it this direction, just to pretend the whole body has rotated in 3D. So this is the essence of this axis angle. So we can represent rotation by rotation about an axis with a certain angle about that axis. And we can do this because Euler tells us so. So let's define not axis. Let's define the axis. The axis with a unit vector along the axis. So we define this axis A, which is some AXI plus AY J AZK. And funny thing about this axis is that if you start to green, no, another purple. Purple is good. If you start, this is your original frame, and you have rotated. So your original frame stays here. Your body fixed frame rotates with the body, becomes this one. In either of those frames, the axis, this A, remains the same. So these A, X, A, Y, A, Z are the same, and they remain constant in both body fixed and I don't want to call it inertia and fixed frame, just fixed or original frames. So it is very convenient to just don't worry about are we talking about the body fixed frame? Are we talking about the fixed frame? Which frame it is? Doesn't matter. The axis actually remains the same. And you can kind of visualize it. So the entire body is rotating about a certain axis. So from the perspective of the body, that axis isn't moving or isn't changing. And that's why they are the same. And this is a unit vector. So A is, oh, what did I? A squared, X squared, AY squared, AZ squared equals 1. Equals 1. And so I have three values, AX, AY, AZ, that I need to define the axis. And the fourth one is phi is the angle of rotation about A. And we use the right hand rule. So right hand rule for no, let me write it differently. About A and positive direct. Let me think. Which one's which? Is it chicken or egg? I don't know. Positive direction of both the angle and A, kind of considering together, follows right hand rule. And by that I mean when your thumb points toward the direction of your axis, the positive direction of A, the fingers are the positive direction of the angle. And in this case, we always define phi between 0 and 180 degrees. So what happens if we go more than 180 degrees? We flip the direction of the axis and then define the angle with the opposite direction phi. So we can always define the angle in such a way that it's between 0 and pi. So it's a very useful kind of intuitive way to define rotations with 4 numbers. 3 representing the direction of the axis, and the 4th one being the angle. This representation is foolproof, doesn't have any singularity or anything. Well, the only possible confusion could be when there is no rotation. So your angle is 0 and any axis would work. But for those simple ones, you can have a convention that whenever the angle is 0, you can arbitrarily choose whatever axis. So it doesn't lead to any complications in when you're computing these variables from a known rotation. The only question remains is, what is the relationship between this, the form of defining rotation, with the previous one that we had? So previously we saw how we can relate Euler angles to rotation matrices. Now let's see how we can relate these axis and angle to rotation matrix. So let's first assume if I know rotation matrix, how can I get my axis and angle? Let's look at that. And for this, let me define my R. Let's pretend I know this R, R11, R12, R21, and so on. Let me write it down. R13, R22, R23, R31, 32, 33. This is my rotation matrix. If I have this, what I can do, take it without proof, that trace of R, which is the summation of all elements along the major diagonal, that is R11 plus R22 plus R33. This one is equal to 1 plus 2 cosine of phi. So from here, you can calculate the angle of rotation. And to find the axis, it's going to be a little long, but AX is going to be 1 over some value D that I will define soon. R23 minus R32. Your AY is going to be 1 over D, R31 minus R13, and AZ is 1 over D of R12 minus R21, and D in this case is square root of all of these squared. R23 minus R32 squared plus R31 minus R13 squared, R12 minus R21 squared. And this is how you can find your angle and the direction of the axis if you know the rotation matrix. Going the other way, if you know axis angle, how can you go to rotation matrix? To do this, let me define a couple of notations. So R, my rotation matrix, I can write it as summation of 2 matrices, RC and RA. I'm sorry, RS and RA. RS is a symmetric matrix, and RA is anti or skew symmetric. This is S. Skew symmetric. Now remember we had it in one of the previous videos. Symmetric is RS transpose equals RS, and skew symmetric is RA transpose equals minus RA. And for any matrix that you may have, you can very easily find these two. So R is 1/2 R plus R transpose plus 1/2 R minus R transpose. So this one is your symmetric part. This one is your skew symmetric part. And with these definitions, it is slightly easier to work our way from axis angle to find the R. The symmetric part is cosine of phi times identity matrix as 3/3 version plus 1 minus cosine of phi, and I'm going to write it as A times A transpose, and A is the vector, but I'm writing it in matrix notation. So this is AX, AY, AZ multiplied by the transpose AX, AY, AZ. So this one is also a 3/3 matrix. So that is the symmetric part. The antisymmetric part is sine of phi times a strange looking matrix, so it is 0, AZ minus AY minus AZ 0, AX AY minus AX 0. Let me see if I have it right. Yes. And this is a very common form that shows up often. And let's have a notation for it. If you have your A, which is AX, AY, AZ, that kind of vector, you can define a skew symmetric matrix based on that vector in such a way. So in a simple way, it's sine of phi A tilde. So if you know your matrix, your axis and angle, you can use this and that to construct your rotation matrix. So it's very good, this method of defining rotation based on a single axis and a rotation about it. Very intuitive, doesn't have singularities or any issues. Kind of easy to work with, not as maybe easy as the rotation matrix itself, but it is a lot more intuitive, I would say. And yeah, that is all I have for this video. In the next video, we'll see a very similar and related formulation. Again, work of Euler. It's called Euler parameters. So until then.